Okay, and here we are, lesson 10, continuing our discussion of motion in two dimensions. And we looked at relative velocities and kind of adding velocity vectors. And now we're going to investigate something called projectile motion, which is the motion of objects as they move in two-dimensional space. And until this point, we've really looked at the motion of objects with travel in one dimension. So cars that are either accelerating or moving kind of left or right, or north or south, or east or west, or up or down. Okay, but through the use of vectors, what we're going to do is extend our study of motion now into two dimensions. So looking at things that move left and right and up and down, and do so simultaneously. So let's begin by discussing parabolic motion or projectile motion. And we're going to look at two different cases. Let's say you're out in the middle of in the middle of space. So there's nothing around you, there's no planets, there's nothing. You're in the middle of empty space, so there's no gravity anywhere. And if you were to throw a baseball, it will leave your hand and travel in a straight line forever. And so the position vector of the ball or the motion of the ball would be just a straight line if you're in outer space. But on Earth, we know that that doesn't happen. When we throw a ball on Earth, it doesn't travel in a straight line. It travels in an arc. It kind of falls to the ground. And that's a major difference. And of course, that's because of gravity. And we know that it's because of gravity. But the term projectile motion is really used to describe events where an object moves under the influence of gravity only and is not self-powered. Okay, so rockets or anything like that really don't travel in projectile motion because those things are self-powered. But a baseball, for example, travels only under the influence of gravity as soon as it leaves the thrower's hand. So let's take a look at the motion, this kind of projectile motion, and look at it very specifically because we can make a couple of observations. The first observation that we'd make is that the ball does not change its horizontal velocity. Okay, so we're neglecting air resistance, but virtually in the x direction, in the horizontal direction, there's no acceleration. Once it leaves the pitcher's hand, it travels with the same horizontal velocity indefinitely. We do know, though, that the velocity in the downward direction, so in the vertical direction, gets larger due to the acceleration of gravity, because gravity accelerates things, as we know, towards the Earth. And the trajectory of the ball would kind of look like this. And so the blue line kind of represents the resultant velocity. But we can draw the pieces that make up that resultant velocity. So here's all the horizontal velocities. So from position 1 to position 2, position 2 to 3, position 3 to 4, position 4 to 5, the velocities in the x direction are the same. But what do we see with the velocities in the y direction? Well, they start getting larger in the downward direction because we have an acceleration from gravity that's downwards. What we want to notice is that each horizontal component is constant, but each vertical component of velocity increases. And of course, we've said before, that's due to gravity. We also know that the angle that we launch a ball, or a projectile, or really anything in general, also affects the path. Because you know that if you throw a ball, think about baseball, if you throw a ball without very much of an angle, it doesn't go that far. If you throw a ball in a pop fly, like right up in the air, it doesn't go that far. the range, which is the horizontal displacement in x, is greatly affected by the launch angle. And what you'd actually find is that in a launch angle of 45 degrees, so right halfway in between the x and the y direction, you get maximum range. And that's something that we'll consider a little bit later. And here's two diagrams to kind of illustrate that. Here's a thought experiment. Let's say you and a friend each have a tennis ball. Okay? At the exact same moment and at the exact same height above the ground, you and your friend both release your tennis ball. You throw your ball perfectly horizontal. So you actually throw it with a horizontal velocity, perfectly horizontal. Your friend simply releases their ball from rest. Okay, so you guys are standing at the exact same spot. You throw it horizontally. Your friend doesn't do anything. They just release it and drop it to the ground. Okay, they release it from rest. Whose ball hits the ground first? And of course, in class, we talk about this and we kind of ask for thoughts. So, think about what you think is going to happen. And there's a couple of things that could happen. Well, you throw your ball horizontally. Maybe your ball hits the ground first. But you may be thinking, well, it travels a greater distance, which of course it would. So maybe your friend's ball hits the ground first. So what's the answer? The answer is, of course, if we neglect air resistance, both balls hit the ground at the same time. There's no acceleration in the x direction. And so even with an initial x velocity, the time to hit the ground is the same. And of course the question is why? Why is the time to hit the ground the same? And if you think about the distance between your ball and the ground and the distance between your friend's ball and the ground is the same. And because the acceleration of the two balls is the same, they're both being pulled to the ground by gravity at a certain acceleration, that's the same. They both have no initial velocity in the downward direction because you released your ball perfectly horizontal. Well, then they both must hit the ground at the exact same time. So think about the equations of kinematics that you'd use to show that. Let's take a look at an example so we can actually start using some of these equations. A baseball is thrown vertically at 35 kilometers per hour. Baseball's thrown horizontally at 35 kilometers per hour. Let's calculate the velocities in the horizontal and the vertical direction at 1 second and at 4 seconds. And then what's the final velocity at each of these times? Okay. So here's our little diagram. We got the baseball at the initial spot, you can see there. 1 second later, it's traveled a certain distance. And then 4 seconds later, it's traveled a farther distance. Let's calculate horizontal and vertical velocities for each of these positions, and we'll work on the final velocity. So we know that initially, V1 is 35 kilometers per hour, but it's horizontal because we say that the ball is thrown horizontally. So you should be thinking, oh, that's a velocity in the x direction. There is no velocity in the y direction at this time. And there we have t equals 1 second and t equals 4 seconds. So now we're kind of on the same page, we got everything. Let's first, because we're talking about seconds and we've got a velocity that's in kilometers per hour, let's convert that right away. 35 kilometers per hour, there's 1,000 meters per kilometer, 60 seconds in a minute, and 60 minutes in an hour. So if we do the conversion, 9.72 meters per second east. All right. So first of all, let's just say this in general. What do we know about horizontal velocities? Because this is going to tell us. With a projectile, the horizontal velocities always are the same. And you should be saying that. Oh yeah, that's right. Because we know that with a projectile, Where's the acceleration? The acceleration is down because gravity's pulling the ball down. There is no acceleration in the horizontal direction, so it means, oh, okay, so the x velocity is going to be the same at the beginning, at 1 second, at 2 seconds, at 3 seconds, at 4 seconds, at 10 seconds. The x velocity, the horizontal velocity, is always the same. So let's divide the remainder of this into kind of 3 separate sections here. Okay, so here's our 3 little separate sections. This is going to help us to organize our solution. And so let's look first at the horizontal velocities, because they're the easiest, because we know they don't change. At t equals 0, our horizontal velocity is 9.72 meters per second. At t equals 1, our horizontal velocity is 9.72 meters per second. At t equals 4, our velocity is 9.72 meters per second. So this is one of the important things about projectile motion, is that the horizontal velocity of the projectile never changes. It's always the same. And so there it is. Now, though, we know that the ball's being accelerated in the vertical direction. So let's take a look at now what the vertical velocities are going to be. Well, at t equals 0, the velocity in the y direction is 0. Because it's launched at 35 kilometers per hour. Yeah. But that is a horizontal velocity. So what we're doing here is we're actually splitting the question into 2 parts. One part looks at horizontal velocities, and one part looks at vertical velocities. And this method of splitting the problem into horizontal and vertical directions is going to be an approach that you'll take to solve all kinds of projectile questions later. So we know the initial y velocity of this specific projectile is 0. Let's find out what it is then at 1 second. Okay, so there's a little arrow to just remind you why that vertical velocity is 0. So here's t equals 1. And let's use one of our kinematics equations, v2 equals v1 plus at, but this is in the vertical direction. Okay, so what's v1 in the vertical direction? 0. What's the acceleration in the vertical direction? Well, it would be 9.8 meters per second squared. That's the velocity due to gravity, or sorry, the acceleration due to gravity, and it's in the downward direction, so we'll give it a negative. And of course the time is 1 second. So after 1 second, it's gone from 0 to 9.8 meters per second, and it's in the downwards direction. So there's v2 at time t equals 1. What about at time t equals 4? Well, let's do the same thing. We want to know v2, so really the second velocity, but at 4 seconds. v1 we can still say is 0, but now instead of subbing in 1 for time, now we're at 4 seconds. So the downward velocity at 4 seconds is 39.2 meters per second. And so what we do is we can say, oh, okay, so now we know what our x component of velocities are, and now we know what our y component of velocities are. And so really we've answered the first part of this question, calculate the velocities in the horizontal and vertical directions. Now what we want to do is we want to say, okay, so then how does the overall velocity change? And this is where our use of vectors comes into play. Because just like we did with displacements and stuff like that, we now have a horizontal velocity and we have a vertical velocity, and we can put these two things together using vectors to find a total, and we can find an angle. And so here's a little diagram of t equals 1 second. So we have a horizontal velocity of 9.72 and a vertical velocity downwards of 9.8. And so we can use the Pythagorean theorem to find the final velocity. And it ends up being 13.8 meters per second. We can also find the angle that this velocity would be at. Tan theta equals 9.8 over 9.72. And if we take the inverse tan of that ratio, we find that the angle theta is 45.2 degrees. Okay, so we would report this then, because it's a vector, we need to report the direction. So we'd say that the final velocity is equal to 13.8 meters per second, and it's in a direction of east, 45 degrees down. Or you could say east 45 degrees south, or you could say right 45 degrees down. Any of these combinations is just fine. So on your own, try the last part of this problem, which is to find the total velocity, the final velocity at 4 seconds. Try that on your own using the exact same method. What would you expect? You'd expect it to be a greater velocity in V final. V final would be higher than 13.8. And you'd expect that it would be at an angle greater than 45 degrees. Okay. Here's example 2. An arrow is shot from a height of 20 meters with an initial horizontal velocity of 18.0 meters per second. How far in the horizontal direction will the arrow fall to the ground? Another way of asking this question is, what's the range of this arrow? So now we're actually looking for not a velocity, but a displacement, because how far indicates a displacement. So here we have a little diagram. We got, somebody standing on, I don't know, a 20-meter high cliff, and they fire this arrow. And of course, the arrow travels in parabolic motion until it hits the ground. So again, first of all, before we do anything, we should say, okay, yeah, we're going to say up is positive as per our convention, and we're going to say that east is positive or right is positive as per our convention. Okay? So that's the first thing. Let's take a look at what we know. We know V1 in the x direction, and we're going to call that V1x, right? So we know V1 and we know it's in the x direction, and it's 18 meters per second. We also know V1y, and it's not listed here, but of course, what is V1y? And you should be saying to yourself, oh, V1y is 0, because it's launched with a horizontal velocity. We know that the arrow, basically, we're looking for the distance that it's going to take for the arrow to hit the ground. So we know that it starts D1, its initial displacement in the y direction is up in the air 20 meters. And what's its final displacement, D2, in the y direction? We know it's 0, because we're looking for the point at which it hits the ground, and we're calling the ground 0. We also know the acceleration in the y direction, AY, and it's down 9.8 meters per second squared. So that's everything that we know. How long will it take for the arrow to hit the ground? Because before we can figure out how far the arrow is going to go, we need to figure out how long it's going to take to get there. And this might be something that's useful. So let's investigate. Well, let's take a look at equation number 3, kinematics equation number 3, but only in the y direction. And so this is what I'm doing. I'm kind of separating the problem out into the horizontal components and the vertical components. Because it's important to note that we don't ever want the horizontal and the vertical to come into contact with each other. They can't, an x can't make its way into a y equation, and a y can't make its way into the x equation. All right, it's like Romeo and Juliet, right? The Montagues and the Capulets. They can't, never can they mix, and that's the same with x's and y's. All right. So how long will it take the arrow to hit the ground? Well, let's solve for t. We know that the change in displacement in the y direction. Okay, we know that it's negative 20 because it goes from 20 to 0, so it's negative 20. The arrow is going to fall 20 meters. We know that the initial velocity in the y direction is 0, so that's going to wipe out that term altogether. We know that the acceleration is down 9.8 meters per second squared. So this equation now actually becomes pretty straightforward. We can solve this no problem because this is just a simple little quadratic. And what we find is that, of course, t squared is equal to 20 divided by 4.9. And when we take the square root of that, of course, we get plus or minus 2.02 seconds. But because in general, the type of physics that we're working with, a negative time doesn't make a lot of sense, we actually don't need the negative root. So what this has just told us is that, hey, this arrow falls to the ground in 2.02 seconds. Okay, that's good because now we have this other piece of information, and it's time. And unlike the x's and the y's, which have to stay with the x equations and the y's stay with the y equations, time can move back and forth. Right? Time is a friend to both sides. And so time can kind of show up in the x equations, and it can also show up in the y equations. So now if we know that it takes the arrow 2.02 seconds to go from 20 meters to 0 meters, we can now find out how long it takes for the arrow to travel the same distance but in the x direction. Okay, so how far will it go in x in 2.02 seconds? Well, here's again equation number 3. But is there an acceleration in the x direction? Does the arrow accelerate in the x direction? And at this point, you should be shaking your head, and you should say, no, the arrow does not accelerate. It's a projectile. Projectiles don't accelerate in the x direction. They only accelerate in the y direction. So that term, that final term there, the 1/2 axt squared, becomes 0. We know that the arrow starts out at a horizontal displacement of 0. And we know that it goes some distance d2x. So all we need to do is multiply our 2.02 seconds, times the 18 meters per second, and we find that the arrow travels 36.4 meters in the x direction. And that's it. More projectile motion questions tomorrow.